Bronsted-Lowry definitions, it was kind of splitting these first few sets of questions up was somewhat artificial, but at least this now sticks a label in there. So now instead of thinking that an acid goes to H+, it goes to H3O+ in water. So 0.05 molar solution weak monoprotic acid is 47% ionized. That's actually pretty good weak acid, isn't it? What's the Ka value? Well, here's the equation. HA plus H2O, firstly going H3O+ and HA minus. Okay, we know that it's a weak acid, which means we have to set up an equilibrium consideration. Okay, we know that the Ka value is the equilibrium H3O+, which is X, times the A minus, which is X divided by the HA, which is the starting concentration, 0.05 minus X. Okay, now we know it's 47% ionized. So what that tells us is that 47% is the amount that's ionized, X, over the starting amount, 0.05 times 100. Okay, in other words, we started with 0.05, 47% of that reacted at any given time. So throw all that in, X is 0.0235, throw that in to all of these equilibrium values, in particular into the Ka value, and our Ka is equal to 0.021. So Ka value, not a huge big number, 0.021, but even with a Ka value that is of that size, look at that, 47% ionized. So in other words, nearly half of the acid was actually ionized. 0.1 molar concentration unknown acid, pH is 5, calculate the Ka. But again, here's our general acid equation, HA plus H2O, reversibly going to H3O plus A minus. Generate the SK chart. We start at 0.1. None of that at the start. Do notice there's none of those at the start in our normal approximation. X reacts, so we let minus X change for the HA, make X of each of those. So at equilibrium, the 0.1 minus X, X and X. Now, Ka is, of course, concentration H3O plus times A minus divided by the concentration of HA. We want Ka, so we somehow know all of these, and all of these are now related to X. So somehow we are need to know what X is. Okay, well, let's look at what else they tell us. They tell us that the pH is 5. Okay, well, if the pH is 5, that's minus the log of the H3O plus at equilibrium is 5. In other words, the H3O plus at equilibrium is 1 times 10 to the minus 5. Well, the equilibrium H3O plus is also X. So in other words, X equals 1 times 10 to the minus 5. Pop that in everywhere that you see in X. So Ka, 1 times 10 to the minus 5 for the H3O plus, 1 times 10 to the minus 5 for the A minus, 0.1 minus 1 times 10 to the minus 5 for the HA. And that gives us 1 times 10 to the minus 9 to one significant figure. KHCN, 5 times 10 to the minus 10. What's the pH? 0.050 molar HCN. Well, here's our reaction. HCN plus H2O, reversibly going to H3O plus CN minus. Set up the SK chart, very standard format. We've got 0.05 molar HCN, that's the start. None of that, none of that. X of that dissociates, giving us XH3O plus and XCN minus. So there's the equilibrium values. Throw those in to the K expression. So Ka, we're told, 5 times 10 to the minus 10. It's the H3O plus, which is X, Cn minus, which is X, HCN, which is 0.05 minus X. Now at this point, we could multiply out to get a very scuzzy looking expression, but what we do is we think as chemists. We say that 5 times 10 to the minus 10 is very small, and if it's so small, that means that at equilibrium there won't be very many products, and if there's not very many products at equilibrium, X must be small, and maybe X is small enough that 0.05 minus X is about 0.05. So let's throw that in. It's 5 times 10 to the minus 10 stays the same. X and X stay the same, because if we make those 0, well, then we've got the whole mess of the thing. But instead of 0.05 minus X, we just got 0.05. Multiply that out. X squared is 0.05 times the 5 times 10 to the minus 10. x comes out to be 5 times 10 to the minus 6. I said minus, didn't I? Minus 6, 5 times 10 to the minus 6. Now you must always check your assumption. And the way we check our assumption is we take the value of x, we divide it by the number that we said it was small compared to, so in other words 0.05, multiply it by 100. So essentially we're determining the percent error in ignoring x. And when we get that here, we get 0.01%, which is very, very small. All we need is less than 5%. So now we go back to the question. pH is minus the log of x, where x is 5 times 10 to the minus 6. We're happy with that. And that comes out to be 5.3. Let's do another one of those. pH 0.3 molar benzoic acid, Ka 6.5 times 10 to the minus 5. So benzoic acid is C6H5COOH, but let's just call it HA because that's all we're interested in after all. It's the fact that it's an acid. Set up the SCA chart, 0.3 molar benzoic acid there, usual format. Throw it into the K value. And so we get K 6.5 times 10 to the minus 5, x times x, those x's there, divided by 0.3 minus x, that there. Again, 6.5 times 10 to the minus 5, pretty small. At equilibrium, therefore, few products, thus x is small. So in this case, 0.3 minus x is about 0.3. Substitute that in, multiply it out, and we get x is 4.42 times 10 to the minus 3. Now check it, okay? So take x, 4.42 times 10 to the minus 3. We divide it by the number that we said was big, 0.3. Multiply by 100, so now we got the percent error. So 1.47%, not nearly as nice as in the last question, but that is still less than 5%. So therefore our assumption is cool. X H3O plus is 4.42 times 10 to the minus 3. We're happy with that value of x. So the pH is minus the log of that, or 2.35. Now, your teachers, by necessity, because of the A-level thing, essentially say we're always going to assume. So if we're always going to assume, all we have to do to get x, to get the H3O plus, is we take the Ka times the initial concentration and then square root it. And that would have worked quite happily for our last two questions. Now, of course, we leave out the whole thought process here. We leave out the check of the assumption. We just leap straight to here and solve it. And that works most of the time. But think about this one. Calculate pH 0.02 molar solution of iodic acid. Look at the size of that Ka. That is not small by any stretch of the imagination. So anyway, iodic acid, HiO3 plus the usual thingy, SCA chart, usual thingy, 0.02 there, minus x, x, and x. Ka is x times x over 0.2 minus x, and Ka is 0.17. This is not small. This is not small. Shall I say it again? This is not small. This is bigger than that initial concentration. This is not small. We cannot make the assumption. So multiply it out, 0.02 minus x times 0.17 is x squared. So notice you can't just take 0.02 times 0.17 because you've got that x in there because x ain't small. Multiply it out and we get this lovely looking expression here, which we then solve as a quadratic equation. Minus b, so it's minus 0.17, plus or minus the square root of b squared, 0.17 squared, minus 4. A is 1 times c minus 0.0034, all over 2a, which is 2. X is 0.018, or it could also be minus 0.188, because remember, anytime you solve a quadratic, two roots. However, x is a concentration, and you cannot have a negative concentration. So x is 0.018, pH is minus the log of that, which is 1.74. Now, if you were to try to calculate it using your other way, you would not get anywhere close to 1.74. For your A level, feel free to square root the two numbers multiplied together. But always, always have at the back of your head, you've got to be very, very careful. So I like this question because it's a twofer. The end, what's the pH? 0.05 molar solution of HX. Well, of course, we've done that 3 times, but to get the pH, we need to know the Ka. Nowhere do I tell you the Ka, but in that first sentence, I give you the information to get the Ka. So anyway, let's plug it through, see how far we get. We can write the equation out for HX, and from that, we can get the K value. Now let's use the first sentence that when we have a 0.1 molar solution of this HX, it's 3.5% ionized. So in other words, 3.5% or 0.035 of this 0.1 turns into H3O plus and X minus. So the concentration of H3O plus equals the concentration of X minus is the 0.035, that's the 3.5% times 0.1. which is of course 0.0035. So let's plug that into the Ka value. Concentration H3O plus 0.0035, concentration X minus 0.0035, and then of course concentration of HX is the 0.1 with which we started minus the 0.0035 that turned into the H3O plus and X minus. Plug that through, Ka is 1.27 times 10 to the minus 4. Now let's go to the second sentence here. Set up our SCO chart. We got 0.5 molar HX, so 0.5 minus X, and then X and X there. Plug all that in to our K value, knowing that Ka is 1.27 times 10 to the minus 4. Now at this stage, much easier if we can assume, so let us do so. If we assume, then we can ignore that X, so we get 0.5 times 1.27 times 10 to the minus 4 equals X squared. So this is now where you would be with the A-level assumption. X is 0.00797. Check the assumption. 0.00797, excuse me, divided by 0.5, the number we said was big enough, times 100 is 1.6%. That's fine, it's less than 5%, so X is indeed 0.00797. pH is minus the log of that, because the pH is minus the log of the H3O plus, which is X. And so pH is 2.1. So that was a nice question in my mind that pulls together both aspects of these type of equilibrium questions. The first one where you're asked for K, so you're effectively told X, which I've done here with the percent ionization. And then the second one where you know what K is, but you're asked effectively to calculate X, calculate the pH. Now, big thing that came in with Larry Bronsted, was the idea of conjugates. Which of the following is not a conjugate acid-base pair? Well, conjugate pairs differ by H+. The acid has it, and the base does not. So as we go through here, H2O, H3O+, that's the base, that's the acid, because the H3O+ has that extra H+. SO4 2-, HSO4-. This one has the H+, so it's the acid, SO4 2-, doesn't, so it's the base. HCl, Cl-, HCl has the H+, so the acid, Cl- doesn't, so it's the base. This one here, tougher to figure through, but H2 and H, and you got minus and 2-, so this one has an H+, this one doesn't. This is the acid, this is the base. These two here, however, differ by not one H+, but two H+. So therefore, this is not a conjugate acid-base pair. H2CO3, when it's an acid, makes HCO3-, which is its conjugate base, and then HCO3- is amphiprotic, so its conjugate acid is H2CO3, and the conjugate base of HCO3- is CO3-2-. So difference there, because 2H+, because this is a diprotic acid, and this is the second conjugate base that comes from it. Same question, same concept. They differ by H+, NH3, NH2-, acid, believe it or not, and its conjugate base, acid, conjugate base, acid, excuse me, conjugate base and acid there, because the H2SO4 has the H+, acid, conjugate base, but HCl and H+ differ by Cl-, so therefore they are not conjugates. Acid HA, K value 1 times 10 to the minus 1, in other words, nice big K value. At equilibrium, solution is acid found at concentration 0.1 The concentration conjugate base is 10. What's the pH of the solution? So there's our acid dissociation expression, for which the K is 1 times 10 to the minus 1. Break that down, and there's the K expression, but everything we're told is that at equilibrium. So plug it in. At equilibrium, Ka is 1 times 10 to the minus 1. At equilibrium, solution of this acid is found to have the concentration HA is 0.1. That's at equilibrium. Concentration conjugate base at equilibrium is 10. What's the pH of the solution? Well, the only thing we don't know is the H3O plus. Multiply that out, the H3O plus 0.001, pH minus the log of that, which is 3.